the message from Lawyer Network is start this webinar. Hi everyone, welcome to our mobile LiDAR webinar. The Ontario Public Works Association Right-of-Way Management Committee is pleased to announce that going forward, it will be letting arms with the ASCE, the American Society of Civil Engineering, the Ontario chapter of the Utility Engineering and Survey Institute, known as UESI, to co-host the annual Right-of-Way Management Conference. For those of you who may not be familiar with the UESI, we are linked to the 2020 Right-of-Way Management webinar series and future conferences. The OPWA Right-of-Way Management Committee and UESI Ontario chapter jointly would like to announce that starting in 2020 and going forward, October will be the Right-of-Way Management Month. The intent of the Right-of-Way Management Month is to promote and to bring greater awareness through education to many challenging issues associated with the management of the public right-of-way. For October 2020, free educational webinars on right-of-way management and associated topics will be offered every Tuesday and Thursday. If you haven't had the chance to check out all the webinars available, please visit right-of-way management, rowmanagement.ca. Registration for future webinars is still open. Prior to starting today's seminar, I'd like to go over a couple housekeeping items. All of the delegates will be muted throughout the webinar to eliminate background noise. I'm sure many of you have experienced that during the pandemic era and the Zoom era. A QA will occur at the end of the presentation if the time permits. The QA tab is on your screen, so you can actually ask questions and forward questions to the facilitator. Hi, Ophir. And the webinar is eligible for the OACETT CPD program as a partial 1 hour fulfillment of the full day informal course self-directed study. A proof of registration and a short summary of what you learned need to be submitted to OACETT for the webinar to qualify towards your CPD. Today's webinar is mobile LiDAR, which is very exciting. And our presenter today is Mr. Peter Hedstedt, who I have had the pleasure of knowing for many years now. Peter is, he's worked as a field surveyor in Canada, Africa, and the Middle East since the completion of his degree from the University of Calgary in 1987. Since 2001, he's been promoting the sale of LiDAR and other survey technologies. He now works as business development manager for JD Barnes Limited and its subsidiaries. You may have heard of them before. Including First Base Solutions and On-Site Locates with a focus on geospatial solutions. Peter's full bio can also be found on our website. And with that, I will let Peter take this away.
Great, thank you very much, Kate.
Peter, you might want to start your video as well.
Oh.
So you can see your lovely face.
Bear with me. There we go.
Perfect.
Everybody can see my screen, hopefully. Can you see my screen, Kate?
Your screen, correct.
Okay, perfect.
Okay,
all right.
I'm gonna mute myself now.
Thank you very much, Kate. It's great to have you moderating this webinar, given your knowledge and background in mobile LiDAR. Before I get started, I'd just like to take the opportunity to once again thank the sponsors, as well as OPWA and UAC for making these webinars happen. And also for the management committee, for the ROW management organizing committee, I should say, for inviting me to present. Based on the poll we took at the time of registration, it looks like we have a number of attendees that know some aspects of the technology. I think we have 1 or 2 very experienced, 71 that are familiar with some aspects of the technology, 18 that have worked with some LiDAR data, and 47 that aren't very knowledgeable. So hopefully we have a little something for everybody here today. And I guess towards the end of the presentation, there will also be, during the Q&A session, there might also be another poll question or 2 for you guys to answer. So with that, let's get started. A little bit about JD Barnes ourselves. The company was founded in 1960, and we recently celebrated our 60th anniversary. Although, unfortunately, I think 2020 will be noteworthy for an entirely different and altogether unfortunate reason. Nonetheless, the company, after its establishment, grew organically over the next few decades, partly through the establishment of a photogrammetric mapping operation in the early 70s, which eventually led to the creation of First Base Solutions in the year 2000, which became a wholly owned subsidiary. They focus on geospatial data acquisition and dissemination, basically the GIS and mapping arm of JD Barnes. This was followed by further acquisitions over the subsequent years. In fact, I think Barnes did their last one in 2019. And it was basically to expand our geographic reach and scope of services. At the same time, Barnes has always embraced, I guess, technology that would help productivity in both the field and the office. And with that in mind, they initially invested in LiDAR back in 2012 with the purchase of their first Faro laser scanner. It's a terrestrial or tripod mounted scanner. And they did a considerable amount of R&D to ensure that our workflows would yield the most accurate survey grade georeferenced results. And our experience over the years with terrestrial LiDAR gave us the further confidence to invest in mobile LiDAR more recently. And it is quite a substantial investment. There we go. Our largest division within JD Barnes is the Geodetic and Engineering Surveys Group. Essentially, geodetic surveys provide a uniform reference system for all desired land-related activities, while on the engineering surveys side of things, they support the design and construction activities of both small and large infrastructure development or maintenance projects. Because both of these, I guess, application areas are well suited to LiDAR, it's this division then that manages all our LiDAR activities, both terrestrial and now mobile. Also, you know, we over the years, we developed and implemented an extensive quality control program for all LiDAR projects. We had to tweak some of that for the mobile LiDAR, obviously. And then we've also made, I guess, a significant investment in state-of-the-art computing resources, hardware, software, and ongoing staff training to keep up to date or abreast of the latest developments, and thereby ensuring timely and cost-effective, project delivery on behalf of our clients. So, what is LiDAR? Well, many of you may know this already, but it stands for light detection and ranging. This diagram actually depicts the basic principles of the technology, which operates in a similar fashion to sonar or radar, but rather than using sound waves or radio waves, it's using a pulsed laser light. When the laser pulse strikes an object within range, it gets reflected back to the instrument, which basically measures not only the range, but then also measures incrementally the angle of the mirrors in the scanner to provide a 3D coordinate at that point. Originally, scanners used, I guess, time of flight to calculate the range to an object. But that's when they were still, I guess, probably scanning at less than a rate at less than 50,000 points per second. As the scanners grew in speed, and currently some of the fastest can scan at 2 million points per second, a technique called waveform digitization needed to be introduced. Now, I'm not a physicist, so I'm not going to get into waveform digitization, but if anybody's interested in learning more about that, I'm sure you can find some stuff online about it. Excuse me. Let's look at, I guess, next, some LiDAR applications, typical LiDAR applications. I originally developed this slide for our terrestrial LiDAR, but a lot of these applications are crossovers between terrestrial and mobile. And what I've done is those that are also applicable to mobile, I've indicated with an asterisk. So the first on the list is architecture or BIM. This is actually probably one of the fastest growing areas for LiDAR because it feeds, I guess, the as-built data back into the original theoretical BIM model. And BIM is more a process that's used not only during the design and construction cycle, but it's meant to be used also during the maintenance and operation phase throughout an entire building's life cycle. So having accurate information and not just theoretical information is vital to I guess the benefit of having a BIM model. Another application that was developed for, or that came about once LiDAR was developed, was heritage conservation. There's actually a number of organizations out there that are going around and actually scanning archaeological and historical sites as a way of digitally preserving that for perpetuity. So a lot of these sites are in conflict zones or in areas that are prone to natural disasters. So having these digital analogs, if you like, of these sites is incredibly valuable. If anybody's interested in checking some of this out, I think it's CYARK, CYARK. Look them up. Transportation infrastructure is an area where LiDAR shines, and in particular mobile LiDAR. And we'll show some examples of this before, but even before we invested in mobile LiDAR, we were already using our terrestrial LiDAR for doing bridge and overpass scans as part of the OSIM, I guess, program. Plant and process. This was actually one of the original applications that LiDAR was developed for. This was one of the original companies that developed this was a company called Syra Technologies, and they were in Silicon Valley, and they were located not far from Chevron's U.S. headquarters. So they pitched it to Chevron, and Chevron joined on board as an early beta tester for this technology. To use it on some of their plant or refinery facilities. And they quickly determined that it provided an incredible amount of benefit for, I guess, brownfield work within these facilities. Asset management and facilities maintenance. This is certainly an area that where both types of LiDAR will shine. I'm aware that there's some, I guess, utility companies already that are contracting out LiDAR more at a mapping scale, but to catalog a lot of their plant assets, above ground plant assets along the right of ways. Topographic surveying, and we'll show some examples of that afterwards. Deformation analysis. This is more suited to terrestrial or tripod mounted LiDAR. And it's mainly because of the, I guess, the accuracies you can achieve with a tripod mounted or static LiDAR versus a mobile LiDAR. You're talking on the order of 2 to 3 millimeters, whereas mobile LiDAR, it's more like 1 to 2 centimeters. For deformation analysis, you definitely want that millimeter level accuracy. Quantity surveys is one that's applicable to both types of LiDAR. In fact, I'm aware of a number of companies that use mobile LiDAR in the oil sands mines to do quantity surveys. We also can do construction as-builts. Again, this is for both types of LiDAR. This ties on the terrestrial side, ties in with the architecture and the BIM models, but certainly for infrastructure projects, it would be a quick and convenient way to capture as-built information on those. Forensic investigations. While this hasn't really caught on for mobile LiDAR, it's definitely has some potential. I know both the OPP and the RCMP have invested heavily in terrestrial LiDAR, particularly when it comes to not just crime scenes, but accident scenes. And they use the terrestrial LiDAR to quickly catalog the accident scene, again, because of the level of detail and the accuracy that it provides. And that permits them to clear the accident scene and open the road a lot quicker. Fabrication is another application for LiDAR, although granted, this is more towards terrestrial LiDAR. And the last area I guess I just want to talk about briefly is by providing data for digital twins. I don't know how many of you may have had the opportunity to sit in on Chris Philpott's excellent presentation a couple of weeks ago as part of this webinar series on digital twins. But LiDAR is one of the main tools, along with others, of course, but to feed data into a digital twin. One thing that's I guess come about as part of my research for this presentation is that there's something called a digital twin consortium that was formed through a coalition of industry, government, and academia that are focusing on 4 specific areas for digital twin technology, and those include infrastructure, natural resources, manufacturing, and aerospace. And what they're trying to do is drive consistency in vocabulary, architecture, security standards, and interoperability, excuse me, of digital twin technology. So that's something to look out for as well if you're involved in LiDAR. So what are some of the advantages of using LiDAR? Again, I'm going to just use a slide that was that I borrowed from our terrestrial LiDAR deck, and I've indicated, I guess, with asterisks is well, those areas that apply to both, and it's mainly all of them, really. LiDAR does provide 3-dimensional site information as opposed to a 2D plan, so it contains a lot more context, if you like. Speed of acquisition, you know, we're talking 1 million points per second moving at highway speeds, so we can, or road speeds, so we can really acquire a lot of data. It's non-contact measurement or remote sensing type technology. So in that sense, it's safer in that you don't have to send conventional survey crews out onto roadways. So obviously there's less need for lane closures on street and highway surveys. The completeness of the data. It basically will capture everything it sees. For those of you that are familiar with conventional survey, it's a crew that goes out and picks up point by point, either with GPS or total stations. And you know, for the most part, an experienced crew will get all the data that's necessary. But if you ever miss a critical point, that means you're going to have to go back out into the field and pick it up again. With LiDAR, that's unlikely. It has an unsurpassed level of detail. It does permit the integration of new design elements into existing infrastructure. So, for instance, an example might be MTO or a municipality wants to, in conjunction with MTO, wants to construct a new overpass over a 400 series highway. They can actually design that digitally, and we can scan the surface of the highway, and then you can actually drop the model of the overpass onto the scan data to ensure that you know, from a construction perspective, from a design perspective, that it's going to fit the first time. It is compatible with most CAD and road design software. So Autodesk and Bentley, which are probably the 2 major players, all support point cloud information. And it allows for the ease of sharing and collaboration amongst stakeholders through something we call a web browser bubble viewer. Basically, this allows anybody that's given access to visualize the data. They can go in, pan around, zoom in and out, and take precise measurements of features right in the data set. And lastly, LiDAR does lend itself to AR, VR, and 3D printing. This, I would think, is more with respect to conventional or terrestrial LiDAR, but certainly, as we'll see, you know, there is possibility for using mobile LiDAR in a virtual reality environment as well. So what is mobile LiDAR? Well, it's a process of collecting geospatial data from a mobile vehicle. As a technology solution, it's probably been around for 10, 15 years now. It basically, it's a system that's fitted with an integrated array of time synchronized navigation and imaging sensors mounted on a mobile platform. In addition to the scanner itself, there's a number of camera systems, but I think what's critical to making this system as efficient and effective as it is really the GPS and the inertial navigation system that is integrated into this overall system, which allows the really the accurate determination of both position and attitude of the scanner itself. So you know, in a I guess a terrestrial LiDAR setting, if a scanner is mounted on a tripod and while it's scanning, you bump it even a little, you're going to see zigzags in the data, like a jagged pieces in the data. So imagine putting a scanner on a moving vehicle driving down an uneven road. What really helps create clean data is the fact that both the GPS at 100 hertz, at 100 times per second, and the inertial navigation system at 200 times per second are updating their positions, and then hence the position of the scanners. So we're able to have, I guess, really consistent data that way. I guess over the life of the technology so far, important changes that have occurred over the last decade have really centered around increased speed of the LiDAR sensor, as well as increased speed of the update rates of the GNSS and inertial systems, and then the integration of additional sensors, as well as the streamlining of the data processing in the software. So particular to mobile LiDAR, I think you know, some of the advantages include the ability to quickly capture comprehensive data sets that can be used for multiple purposes. This is a scan that was done of Herb Gray Parkway in Windsor. And typically we capture data at between 50 and 80 kilometers per hour. I guess on 400 series highways, 80 kilometers an hour would be a little slow, so it's definitely advisable to have a patrol vehicle traveling behind, whether it's an escort from the police or your own escort vehicle. It does provide increased safety because it greatly reduces the need for conventional surveys on roadways. You know, if some soft surfaces off to the side of the roadways need to be picked up, sometimes you might get some trees or bushes that obscure some of that, and that can be quickly captured with some infill conventional, but at no time do the survey crews have to ever go out onto the roadway itself. It is a reduced delivery time with the ability to create higher value deliverables. And by that, we basically mean once the data has been collected and processed, we can do most of our feature extraction or topo work from the data in the office, as opposed to leaving it up to our field crews to decide what is critical information to pick up. And of course, the density of the data means we can extract those salient features directly from the point clouds to create those topo plans. And I'll show some examples of that afterwards. When it comes to considerations with respect to mobile LiDAR, obviously accuracy is top of mind. And these systems are accurate when used correctly. Ensuring that the accuracy can be achieved involves the use of GPS base stations, the use of painted chevrons that are surveyed as ground control points, as well as geoid localization to provide accurate elevation data. Complexity is another consideration. While the software does provide batch processing routines, several steps are nonetheless required to be performed in the correct sequence to merge data from the cameras, the inertial navigation system, the GNSS, and the LiDAR sensor. And lastly, for this data to be useful, it needs to be effectively shared throughout the organization. This isn't really an issue with conventional survey data, where even a large file will be measured in the kilobytes of data. But when you're talking about LiDAR, this can become a roadblock when you're dealing with gigabytes or even terabytes of data. Fortunately, Barnes has a dedicated IT department that has set up some specific servers for us and connections to facilitate this. So let's have a look at the system itself. We invested in the Leica Pegasus 2 Ultimate. Basically, the system uses this 360 camera that you see up top here to apply RGBs, or red, green, blue colors to the point cloud. We'll talk a bit more about the 360 camera in a minute. This is a calibration sensor. It checks the calibration and RPMs every time the system is turned on, and when not in use, it retracts and is flush with the surface. I guess the main element itself, the LiDAR sensor, is a Z&F profiler. It is eye safe, has a range of 120 meters, a scan rate of 1 million points per second, and a maximum scan speed of 200 profiles per second. So in 1 second, it can do 200 profiles with 5,000 points in each profile. Pretty impressive. Operating temperatures are spec'd at -10 to +45 degrees Celsius, and it's rated at IP54 water and dust resistant. A couple of comments on those specs. First of all, below zero, we have noted some minor deterioration in the performance of the system, so we don't tend to take it out below freezing. Again, it's a very expensive system, and we want to protect our investment. So typically, our periods of collection are kind of late March to mid to late November, depending on the weather. Also, with respect to dust and water, any types of particulates in the air, whether it's aerosols, water droplets, dust, are going to produce some scatter from the LiDAR profiler, or the sensor, and it's going to make a very kind of busy and congested LiDAR data set. So again, we tend to typically only take it out when the weather is optimal for scanning. Power supply is one cable connection, provides about 10 hours of power. Where there's a solid state drive bay and additional sensor ports here. We'll talk about that in a minute. The roof mount is a part of the system, and it stores complete in one case. It will fit onto most standard roof racks on vehicles. It does permit changing the orientation of the scanner, and that is important for one reason. If the scanner is always perpendicular, or scanning perpendicular to the direction of travel, and you're doing multiple passes in different directions, sometimes it's desirable to actually have it offset from perpendicular to create kind of a crosshatch pattern, to avoid having, I guess, the scan profiles parallel and potentially lining up with one another, in which case you're going to have blank spots on the surfaces that you're scanning. We have a triple band GPS system, RTK GPS integrated. There's a light sensor that provides automatic exposure control for the cameras. We have these additional 4 cameras situated on all sides of the scanner. Those aren't used other than to provide, additional information that can be extracted from those imageries, and I'll show some examples of that after. It has an integrated PC and span module, and it's basically merging data from the IMU and the GPS before that gets downloaded. The IMU is a tactical grade, providing updates at 200 times per second, and the GPS is doing it 100 times per second. I mentioned the solid state drive port. Previous generations required downloading the data via a cable connection, which was onerous, especially if you had very large data sets. The addition of a removable 1 terabyte solid state drive has greatly facilitated the transfer of the raw data to the processing software. We've also got, as I mentioned, 2 additional sensor ports, so you can plug in things like road roughness wheels for measuring road roughness and that type of thing. Oops, come on. There we go. I talked about the enhanced side cameras. There's 4 of them, each of them 12 megapixel. They take 9 frames per second. Onboard camera processing as well. It has a large field of view and is 5 times the quality of the last generation. And here's just an extract. So this would have been the image that was taken from the scanner as it was driving down this road. And because of I guess the quality of the optics as well as the resolution, you are able to get additional information. So if anybody was interested in understanding what pole this was from a asset management perspective, there you have that information that's easily identifiable. The 360 camera is new to the Pegasus 2 Ultimate. It was specially developed by Leica, and they have a long history of R&D into lenses, as they used to be joined with Leica camera as well. This is a 360 spherical camera. It has a high dynamic range, equal quality across the entire lens. So there's not really much distortion at the edges. It is a dual fisheye lens, 24 megapixels. So when you combine that with the other 4 cameras, you're actually getting 72 megapixels of imagery multiple times per second. So you can see how the data adds up very quickly in solid state drive. And it is completely stitchless imagery. And here is basically a sample image. What you see here on the margins are not side streets, but these are actually, this is the street behind us, so 180 degrees in the direction that the vehicle was traveling in. In fact, if you actually printed this out on a strip and joined the left and right edge together to form a circle, then you would have basically a full 360-degree panorama. The Pegasus 2, and I would say most mobile LiDAR systems are vehicle independent, meaning they can be installed on a variety of platforms. So boats, high rail vehicles, road vehicles, ATVs, as well as towed ground penetrating radar arrays for doing simultaneous mapping of subsurface and above ground features in a merged data set. I think T2 had demoed one of these systems. I'm not sure if they ever purchased it or not, but certainly we would love to team up with you to do some, I guess, experimentation on this if you still have it. Ophir, I'm talking to you. In terms of a workflow process, we start off with mission planning. And that, as well as prep, I guess the planning involves determining how many passes need to be made, right, depending on the number of lanes in on the roadway, where to install GPS base stations, as well as where to put and at what interval the chevrons or the ground control points. In terms of mission prep, it involves installation of base stations, installing the chevrons, and actually surveying them prior to the data collection. Data collection involves essentially driving the project. I've mentioned, I think before, typically, if not, here it is, typically on 2-lane roads, we would drive once in each direction. And for wider roads, we would consider a minimum of 50% of all driving lanes. So on an 8-lane 400 series highway, we would probably drive it twice in each direction, given the width and everything, as well as the fact that there would typically be a median in between the directional lanes. Next step would be a GPS base and geoid localization. This is necessary to obtain accurate elevation data. From there, we go to data import, synchronization, or image orientation, and this is all part of a batch process. Timing is the main key relationship between sensors and trajectory. From there, we would generate a 3D point cloud. This, this system by default generates a hexagon point cloud format, but that can be easily converted to industry standard or preferred client formats to work in. And most clients seem to prefer to work with LAS point cloud files. And the last, step in the workflow process is the feature extraction or topo. And our team will typically draft directly from the point cloud data in whichever client spec is needed. That being said, there's a number of QC steps that are important intermediary points at various points in the process. So at this point, we check that the coordinate system and datum are correct, and also that multiple passes are consistent. And I'll explain what I mean by that a little later in the presentation as well. At this stage, we do an examination of the chevrons and a comparison of the detection routines with actual data captured. And then we also check the trajectory and verify the trajectory residual reports. And then lastly, we'll do another QC of the point cloud to conventional survey points captured with a total station or GPS. This is actually also an integral step in MTO requirements, but because we feel it's a valid QC and means of verification, we've also adopted this step in the process for all of our scanning work. So let's look at some sample data, shall we? This is probably what you're all been waiting for. So this is a screenshot of data collected along Conlin Road in Durham, and in particular the roundabout. What's noteworthy about here, you can see as we drove in this way and around the traffic circle, and then came back out and headed back along our original path, you can see that because the scanner picks up everything it sees, it cannot see through or past solid objects, right? So we have a vehicle approaching the roundabout from this direction, and as we pass by, the scanner creates a shadow effect behind that vehicle. Same on this side. What's noteworthy about this, I think, is that it looks like the scanner stopped functioning briefly between here and here, because otherwise it would have filled in this shadow effect. So clearly the scanner was scanning here and created a shadow effect, but it looks like it stopped working here and then, I guess, kicked back in here. This was during an early test as we were getting a feel for the system. I can assure you that we've worked out all the kinks and bugs, and this does not happen to us anymore. This is the same Conlin Road roundabout, but this basically shows how we've extracted the topo features from the scan data. So we did not have to send any field crews out into the field to do this conventionally. This was other than perhaps a few infill points off the road surface here, but most of this was drafted directly from the point cloud. This is some sample data from a multi-lane road. In this sample, we can clearly see the lane markers, right? You can see the height differential from the road surface to the curbs. You can see sidewalks, guardrails, lamp posts, small trees that have been planted in the median, and even might not be entirely clearly visible, but the bicycle lane markings. This was actually a grayscale, but there's various ways you can display the LiDAR data. RGB, so red, green, blue. So you're basically colorizing the point based on the points based on the imagery. You can also do intensity mapping, where it's basically a false color image, and it's based on the intensity of the return of the original LiDAR signal. I think when it comes to intensity mapping, you probably tend to see lane markings and that type of thing a little more clearly, because the white reflects the LiDAR a lot better than the darker surface of the road. Most municipal class environmental assessments do require topo surveys for any construction projects to be performed in the right of ways. And sometimes they're required to be conducted right to the facades of the buildings, the topo surveys that is, on properties adjacent to the site. With mobile LiDAR, if it can see the property, it can capture the data. Bushes and trees, on the other hand, can obscure some of the facades as the technology is line of sight, right? But in that case, just a bit of conventional infill would be required, and we'd be ready to go. And it would still be a lot quicker just doing a few infill shots than trying to do this whole thing conventionally. It provides an incredible amount of detail, and I think I mentioned this before as one of the advantages. And this slide I put in just to highlight this fact, right? You can easily spot where road cracks have been sealed, so pavement condition could be a value-added deliverable from any campaigns where mobile LiDAR data has captured road surfaces. And if anybody's ever driven south on Victoria Park Avenue across Steeles, you'll know how bad sometimes the Steeles can be rutted because of the buses and heavier vehicles that travel along there. Again, if that's driven with LiDAR, that's very easily to map those kind of areas. Once the data has been captured and processed, it's incredibly easy to generate road cross sections from the data set. Essentially, our technicians will basically draw this box across this area and basically segment the point cloud along this line, and then pick a viewpoint, and this is the data that you get. In this example, we have sufficiently detailed data to map the sidewalk extents, so we can see that the sidewalks end here, the top of curb, edge of pavement, width of the median, and even height of the lamp post and sign above ground level. Cross sections can be extracted at any interval or in any direction. In this example, we extracted data at this intersection here, so across this intersection, showing the road profile as well as traffic signal infrastructure and overhead utility lines. This is a movie that we created from a project that we did on behalf of MTO for a divided highway. Just a little disclaimer, this video was not created from the scanner, so if you see the point of view jump off the highway and onto an adjacent road, this is not our mobile LiDAR vehicle leaving the roadway. This is simply our technician panning around from screenshots on his computer as he's moving through the data set. You'll notice that it's a little pixelated, and that's because of the size of this data set. In order to effectively create this video, he had to de-densify the data set, basically decimate it so that there's not as many points in it, or else it would have been a lot jerkier and not as high quality. So that's why it looks a little pixelated. But you can see the amount of detail that we can collect in a very short amount of time. Okay, let's move along. When it comes to accuracy, out of the box, we found we could achieve accuracies in the 3 to 5 centimeter range in horizontal and vertical. When we add in the GPS base station data, we're able to improve this to 2 to 3 centimeters. And then with the use of chevrons or other easily identifiable features as ground control points, we can refine this even further to 1 to 2 centimeters. Obviously, to achieve the best accuracies, we use both base stations and chevrons. And this is a typical, I guess, QC analysis that we would do. So these would be, I guess, the ground control points that we've surveyed based on the chevrons or other easily identifiable features. And then from the point cloud, we would extract the same points, or the coordinates for those same points after it's been processed and georeferenced. And then we can compare the two and look at the level of agreement between them. If they agree statistically, then we can use them in the adjustment. If not, they're rejected and just used as checkpoints. And then, of course, we also do some statistical analysis on this. But you can see that there's typically a pretty good level of agreement between the delta X, delta Y, and delta Z. I mentioned the use of chevrons. So what we do is before we go out and drive a project with our mobile LiDAR, we'll go out and we'll paint a chevron on the side of the road in white paint. Again, because white will appear easily in the scan data. And then the crew that's gone out and painted this will also take a measurement at the very tip of this chevron. So then as we drive this project, we process it, and then as part of the QC process, we'll find these chevrons, extract the coordinates of the point of the chevron in the point cloud, and then do that comparison that you see right here. I also mentioned doing one of the QC steps that we do is matching trajectories. If you recall, I mentioned that for multi-lane roads, we typically drive them in at least once in each direction, oftentimes more. What that allows us to do is basically change the intensity or color of how the points are displayed in the different tracks, and then we can overlay them. So that's what this bar has done, is they've basically created this slice, if you like, and then we can evaluate the degree to which those two tracks line up or agree. And we see here a high level of agreement between those two tracks, so we know that we have good quality data. And then lastly, we can, from the software, we can do positional accuracy plots. Note the scale. I mean, this is 1 centimeter. This would be 2 centimeters here. So even where we have spikes, which represent, I guess, the calibration routines, both static and dynamic of the scanner and the IMU, we're well within the tolerances of the system. And of course, this would be the mission data, and we can see that all mission data is less than 1.3 centimeters in accuracy. Let's look at some data examples now. How am I doing for time? Oh, okay. I should move this along. This is a First Nations road topo. You can see, again, here was a cross-section, road cross-section, but we also did a longitudinal slice that shows the slope in the road. On the right, we have shown, I guess, just to show how clean the data is, this water tower that was extracted as we drove this road. In case you're wondering, the different colors represent different elevations, and that's one method you can use to do point cloud classification to extract relevant data. Yeah, in this summer, we were contracted to do scan the entire downtown campus of Ontario University. Because many of the interior areas of the campus were reserved for pedestrian use, we received permission to nonetheless drive it with a side-by-side ATV rather than our truck. This was quite a complex project and did require some additional infill surveys with both conventional survey methods as well as terrestrial LiDAR. Along the edge of this university campus was a light rail transit, and we were amazed to find that even though we weren't, this wasn't part of the scope, we were able to pick up some very detailed data showing not just the rails and the ballast, but we even managed to capture a train that was going by at the time. And with that, thank you for your attention, and I'm ready to take any questions that might arise. And of course, if there's any follow-up questions that you might have that you don't think of now, please note my email address. Feel free to reach out to me. Always happy to discuss the benefits and advantages of using LiDAR on any project you might have.
All right, everyone. I do believe we have some audience questions for Peter. Peter, thank you so much for that very informative presentation. So I'm gonna kind of punt a few questions to you, and if you guys have any additional questions, if we can't get them through them all today, we'll definitely follow up with an email to everyone that participated in this conference. So Peter, to get started, there's a question here. Does Esri software ArcMap have capability to analyze 3D point cloud data?
I'm not sure about analyze, but it does accept LiDAR data. So I suspect there would be some analytics involved. I'm not sure about mobile or terrestrial LiDAR. I would assume so. I do know that ArcMap can take in airborne LiDAR. And since a lot of times the LiDAR formats are pretty standard, I would assume that yes, you can do that with ArcMap. But I'm not an Esri expert. You're better off talking to your Esri rep about that.
Yes. Several years ago, I did upload some mobile data to ArcMap, but because it's used to having aerial data, terrestrial data tends to be a lot more dense, and so it'll take up a lot more space.
Gotcha.
What is the expected horizontal and vertical accuracy of point cloud data captured from mobile LiDAR technology?
Well, as I mentioned, it really depends on how rigorous you are with your with some of your I guess additional supporting data. But really, we're quite confident that we can keep it within the 1 to 2 centimeter range for both horizontal and vertical, provided we're using GPS base stations and the proper QC methods that I outlined.
Okay. How would mobile LiDAR work on rural roads that have trees from the ditch line to the right-of-way limit?
Well, it's going to pick up everything probably to the trees, and I think I indicated this a couple of points during the presentation that it's not going to see beyond let's say the wall of vegetation. If you need to pick up soft surfaces beyond that where the LiDAR can see, that's where you would probably need to do it with a conventional survey. But typically you would it would probably be a lot quicker than if you would still be a lot quicker than if you were to do the whole thing conventionally.
Perfect. Does the system have the capability to capture high resolution images and 3D point clouds simultaneously?
Yes, and that's why they've got both cameras and the scanner integrated into the system. It's the 360 camera that provides the RGB colors to the point cloud, so you can overlay that imagery onto the point cloud and actually colorize it to make it almost look like a pixelated picture, if you like. The other 4 cameras are really just for supplemental information.
Perfect. So as we continue, there's a couple more questions that we're going to ask, but as we continue, we're just going to ask all of the audience members to fill out the poll that was presented to you. It should be popping up on your screen right now. So if you can fill that out as we go along, that would be very helpful for all of us. Thank you so much. Peter, another question. Which software was used to create the LiDAR animation?
I honestly don't know the answer to that, but whoever asked that question, if you'd like to reach out to me, I can talk to our processing technician and get the answer to you.
Perfect. Another question, do you use chevron adjustments just for QC, or those have been used in adjusting point clouds as well as using total station and GPS data?
Yes, so it's not just the chevrons, but if we can identify features in the point cloud, existing features, it could be like a turning arrow, like a lane marker that's been painted on the road, and as long as we know what point of that feature was picked up, we can also use that as a QC. So the chevrons are basically used to supplement maybe existing ground control features that we've picked up.
Another question, how many 3D points does mobile LiDAR capture within a square meter? And what about the approximate cost per square meter of a LiDAR survey?
So the density of the points can be set based on the maximum range you want to go. So if let's say you want the a good point spacing at 25 meters from the scanner, then everything closer would be denser than that, and everything further away would be less dense. So it is variable, and it really depends on the needs of the client and the you know what requirements are for a particular project, how dense we're going to set that. At maximum density, maximum point density, you're going to have a lot of data. You might not necessarily need it. And it is going to slow down both the data capture and the processing if it's extraneous data that you may not need, right? Do you really need 100 million points to you know, measure you know 100 meters of roadway, or will 10 million points do, right? I guess that's the question, right? So.
Here's another question. How well does subsurface LiDAR tie into above ground scans?
It really depends on how well it's georeferenced to the, you know, the same coordinate reference system. So if you're doing a subsurface scan, and I presume this question is related to that GPR towed array with a mobile LiDAR on top of it. Presumably, when you process that GPR data, there would be a way to georeference it to the same coordinate system as the scan data, and therefore you would get a merged data set.
Perfect. Here's another technical question: how the vehicle vibration affects the survey accuracy?
Yeah, I mean, the rougher the road surface, probably the more I wouldn't say inaccurate, but you know, you're going to be probably more hard pressed to achieve the high accuracy, right? Obviously, the smoother the road surface that you're traveling across, the better the data quality will be.
Great. What format does the LiDAR information come in? Is it compatible with regularly used software like CAD and MicroStation?
Typically, yes. I know early on, Autodesk products treated an entire point cloud as an XREF object, right? So you couldn't really segment the point cloud that well, or look at individual points within the point cloud. They've come a long way now. And there's multiple plugins available as well for both Autodesk and Bentley products. But for the most part, I think point clouds have become pretty industry standard, and most CAD software will accept point clouds directly.
Great. Another question, this one on the cost. So somebody has asked what the cost for this service on average would be.
Well, it depends whether it's mapping grade or survey grade that's required. So mapping grade we define as about 10 centimeter accuracy. We don't have to do as many QA QC steps through it. And then of course survey grade would be probably 2 centimeters or less. So the costs vary depending on the grade of survey or grade, whether it's survey or mapping. Typically, mapping would be approximately $1,500 a kilometer, and then on the survey side, our standard fee is $2,000 an hour. It sounds like a lot, but in an hour you can capture a hell of a lot of data.
All right. Can you speak to the level of manual labor required to QC the data and interpret the findings to the specific use case?
I probably am not the right person to ask that, but if you email me, whoever asked that question, I'd be happy to put you in touch with somebody that would be probably happy to discuss that with you.
Here's another question that you may have kind of answered. Are the chevrons connected to any benchmarks, and do you traverse to tie up the chevrons to the data? Yes.
So typically, you know, when we, I guess, like install the chevrons and survey them, we're either with a total station, we will tie into local geodetic control. or with our GPS, we're working off a network which provides RTK corrected positions based on whatever coordinate system and datum we're working in. So typically UTM 17, NAD 83, CSRS.
Next question. What is the average time ratio of data collection versus point cloud generation and data extraction in a moderately complex urban condition?
That's a great question. I'm not sure, but if I had to guess, I would say it's at least 10 to 1. So for every hour spent collecting, processing and extracting data, it's probably 10 hours work.
Okay. The railway survey needs a 2 to 3 millimeter accuracy for the top of the rails. Can LiDAR provide this precision?
I would have to say no, not from a mobile perspective. I know Metrolinx has conducted, I guess, LiDAR surveys using a mobile LiDAR system on a high rail vehicle, but it's more to, I guess, map the corridors that they operate in as opposed to surveying the elevations of the rails. I understand the accuracy required for top of rail surveys, and I would not be recommending LiDAR for that. I would be recommending a precision total station for that type of work.
Next question. How is the collected point cloud data changed by the laser beam attenuation factors like dust particles or water droplets?
Well, any kind of water droplet, snowflake, or dust particle it encounters, chances are it's going to get reflected back to the scanner, which will interpret that as a point in space, right? So it's not actually hitting a surface. So what you would see in the point cloud itself is a bunch of points scattered in space around or throughout the point cloud itself. So yeah, I didn't actually include any examples where we can see that, but suffice it to say, if you were to look at it from a ground level, it would almost look like it was snowing or raining. But the points would be, if it was intensity map, they would probably be yellow or red.
Yes. Okay, the next question. What about subsurface scans on sewer manhole and bell chamber scans integrating into a surface LiDAR scan? So another Sue question.
Yes, in fact, we've done a lot of that. We devised a technique that allows us to lower our scanner into manhole and other utility chambers, and it has the benefit of preventing us from having to do confined space entry. So it's a safer means of obtaining the information, and it's also more complete. I didn't, I guess, show any because this focus was on mobile LiDAR, but we have lots of imagery available from when we did, I guess, utility chamber and manhole scans. So if you want to reach out to me at the email address, I'd be happy to provide you some information on that as well.
Perfect. And last question here for our seminar. Does the LiDAR have a backup battery, and how long can that LiDAR operate on a charge?
I'm not aware of any backup battery. Typically 10 hours battery life is more than ample for all the projects that we've done. It's never been an issue for us. But I'm not aware if there is a backup battery or not. So I'm sorry, I can't answer that question more than that or better than that.
Perfect. And I think that was all the questions that had been put forward regarding LiDAR in the chat. So I know that there was a couple things that, people needed a few more details on. So as Peter said, please reach out to him directly, and I'm sure he'd be happy to answer your questions. Thank you so much, Peter, for that really, really informative and great seminar. That was really interesting. And
I just want to thank the attendees because with all those questions, clearly there was a very high level of engagement, and I certainly appreciate everybody joining in today. And thank you, Kate, for your excellent job moderating.
Oh, happy to do that. It's great. Any excuse to see you is always a good excuse. So
You're a real smoothie.
Just next steps. Our next week's webinars on October 27th, we're doing a 5G small cell webinar. And on the 29th, we're doing a winter operations within the right-of-way seminar. And then we are also doing with Utility Engineering and Survey Institute, the UESI, Utility Engineering and Transit online workshop. It'll be November 3rd and 5th. And you can register at the link below. And it's offered in partnership with CAT, which is the Center for Advancement of Trenchless Technologies, and the UESI. So that'll be a great seminar to attend. And then we also have coming up the Canadian Common Ground Alliance Virtual Summit, the CCGA, and UESI will be sponsoring 10 municipal and provincial scholars. So if you or someone you know is interested in taking advantage of that, please apply at info@uesicanada.org. And we look forward to seeing you guys there. So if that is all the questions that we have today, thank you so much, everyone, for attending. And we hope to see you at the next seminar. All right. Thanks, Peter. Thanks,
Kate.
Thanks, everyone, for coming.
Bye-bye.
Bye-bye.